A very important theorem in this section of our class is Clairaut's theorem, also known as the mixed partials theorem. If our function f of xy, its first partials fx and fy, and its mixed partials fxy and fyx are defined throughout an open region containing the point a comma b, and are all continuous at a comma b, then the mixed partials at a comma b must be equal. That's a really cool fact, and it's a really cool fact that can actually speed up some calculations, because if we have mixed partials and we have continuity at a point and our functions and partials are defined throughout a region around that point, then we can swap the order. One order of finding a partial might be easier than another. Not in this example, but in some examples we might see down the road. W is equal to the natural log of 2x plus 3y. We're asked to show that the partial with respect to the partial of w with respect to x and then y is equal to the partial of w with respect to y and then x. We're actually asked to verify Clairaut's theorem, I suppose, for the values in the domain, right? This function's not defined everywhere. So let's find a partial with respect to x and then y, and then reverse the order and see what happens. So w was the natural log of 2x plus 3y. The partial with respect to x, well, let's see. The derivative of the natural log of u is 1 over u times the derivative of u. Well, that's just going to be times 2 because the plus 3y is a constant. So I have 2 over 2x plus 3y. Let's go on and take a partial derivative with respect to y. Well, 1 over u, and this time, since I'm differentiating with respect to y, times 3. I need to take one more derivative for both, and we're supposed to get the same thing. I'm going to rewrite these using an exponent. I never get tired of watching a mixed partials calculation work out the same, even if in the middle it didn't seem like it would. The partial with respect to x and then y. All right, so I multiply down that minus, again, minus 2 times 2x plus 3y to the minus second times the derivative of the inside with respect to y, so times 3. So I get a minus 6 all over 2x plus 3y. Now I have the partial with respect to y, then x, minus 3 times 2x plus 3y to the minus second times the derivative of the inside, but with respect to x, is 2. And that's just so very nice. I lost a minus over here. I know that's bad. All right, 2 times minus 3 is minus 6. I also lost a square. Oh, no. Okay, everything's okay. I'm just going to let that ride. We all make mistakes. 2x plus 3y squared. So Clairaut's theorem, if I needed both of these calculations, I could get away with just doing one, because the natural log of 2x plus 3y is a continuous function over all of the values in its domain. We could actually write down its domain by saying, well, 2x plus 3y has to be bigger than 0. But I'm happy we've satisfied our problem, and I got my mixed partials to work out nicely.